In this module, we'll begin our journey with probability theory. Probability theory is used to model the physical phenomena which involve uncertainty or randomness. For example, in communication systems, the transmitted signal is corrupted by interference, fading, and noise, which are all random phenomena. Such systems can only be described, understood, and analyzed in probabilistic or statistical terms. In this module, we will learn some terms used in probability theory. The first term that we take up is the notion of a random experiment. Notationally, a random experiment is denoted by script H. A random experiment is a non-deterministic phenomenon, a phenomenon whose outcome is not deterministic, whose outcome is not predictable. Some typical examples include tossing a coin, rolling a die, picking a card from a pack of cards, or to take an example from communications, the conveyance of information in the form of electrical pulses, which are symbolically represented by ones and zeros, constitutes a random experiment. So, transmission of ones and zeros is yet another example of a random experiment. For instance, if we consider tossing a coin, there are two possible outcomes, heads and tails. But before tossing the coin, it is not known whether the coin will show up heads or tails, and therefore the outcome is not predictable, and therefore it's a random experiment. Strictly speaking, a random experiment has to have three features. Number one, the experiment must be repeatable under identical conditions. The outcome of the experiment must be non-predictable, and third and very important feature is that the outcomes should show some statistical regularity if the experiment is repeated a large number of times. If we consider, for example, the tossing of a coin, we can keep on repeating the experiment a large number of times, therefore the experiment is repeatable, and every time it is not known a priori whether the coin will show up heads or tails, and therefore the outcome is non-predictable. And if the coin is tossed a large number of times, on an average the number of times heads will show up is approximately half of the total number of trials. So, some sort of regularity is there, statistical regularity is there. So, tossing a coin, for instance, follow all the three features, and therefore it qualifies to be called a random experiment. The second term that we take is the notion of a trial. A trial is a single performance of the random experiment. So, it is simply a single performance of the random experiment. For example, if we consider tossing of a coin, so the coin toss is called a trial. Or if we consider rolling a die example, so when we roll a die once, that will be called a trial. The next very important term is the sample space. Sample space is denoted by capital omega or S, capital S. It is the set of all possible outcomes of a random experiment. So, it is the set of all outcomes of the random experiment. For example, if you consider tossing a coin, then there are two possible outcomes, heads and tails. We denote them by h comma t. So h comma t then constitutes the sample space. If you consider rolling a die, assuming a 6-faced die, the sample space would be numbers 1, 2, 3, 4, 5 and 6 and so on. The next term is event. An event is simply a subset of sample space. Event is a subset of sample space. Strictly speaking, an event is that subset of sample space which can be assigned a probability. But for our purposes, we will assume that all subsets of the sample space can be assigned probability and therefore they can be called events. So, we will use the terms event and subset of sample space interchangeably. Events are typically denoted by letters A, B, C, D and so on. To consider an example, suppose tossing of a coin, then there are 4 possible events we can identify, 4 possible subsets or events. They are heads, tails, head comma tail, the sample space itself, or the phi, the null set, because null set is the subset of every set. The next term is a very important one, the notion of what we call a sigma field, denoted by script f. It is the set of all events of a random experiment. Or in other words, we can say that it's the set of all subsets of the sample space. For instance, if we continue our coin tossing example, then the sigma field will be a set whose elements are all subsets of the sample space, which are the elementary events h, t, heads, tails, the sample space itself omega and the null set phi. So there are 4 elements or 4 subsets in this sigma field. One important point to note about sigma field is that because we have defined it to be the set of all events of the random experiment and only events can be assigned probabilities, as we shall discuss in some later module, then every element of the sigma field can be assigned a probability. The next term is a probability measure. A probability measure is a function that assigns probability to events. Probability to events. Notationally, we write it as P of some event. This dot denote some event. For example, if we consider the tossing of a coin, the corresponding probability measures would be denoted as P of H, P of T, P of omega, and P of phi. Having defined the notions of a sample space, the sigma field, and the probability measure for a random experiment H, we have the notion of a probability space. So for a random experiment H, we have a sample space which is the set of all possible outcomes, a corresponding sigma field which is the set of all subsets of the sample space, or which is the set containing all the events of the random experiment, and a corresponding probability measure P that assigns probability to each element of F. Then these three together, omega Fp, form a triple or a triplet which we call the probability space, denoted by script P. Just as a coordinate space helps us describe the location of a point in a space, just as a vector space helps us describe a vector, a probability space is required to model random phenomena. We have already described the notion of an event. Now there are a variety of events that we encounter, and it is good to know there are various types. So the first in the list is what we call an elementary event. An elementary event is a single sample point, a single sample point. For example, in coin tossing, heads and tails form elementary events. Then there is a universal event. A universal event is the entire sample space. It is the entire sample space, the omega, because every set is its own subset. The sample space itself qualifies to be an event. The universal event is also called a certain event or a sure event, because the probability of its occurrence is 1, as we shall see in a later module. Then we have a null event. An empty set is the subset of all sets, which is called a null event, denoted by phi. The next term is mutually exclusive or disjoint events. Two events are said to be mutually exclusive if their intersection is a null set. In general, if we consider a listing of events A1, A2 up to AN, then the events of this listing are all said to be mutually exclusive or disjoint if for any pair of events AI and AJ, their intersection is a null set. AI intersection AJ equal to phi for all I not equal to J. For example, if we roll a die and define two events on it, one, the number of dots show up is an even number, and another event that the number of dots show up is an odd number. So these two events are mutually exclusive events. The next term is collectively exhaustive events. Now, events are said to be collectively exhaustive if their union make up the sample space. For example, if we have n events a1, a2 up to an, then they are said to be collectively exhaustive if their union is equal to the sample space. More succinctly, we can write union I equal to 1 to n, ai equal to omega. A given listing of events can be both mutually exclusive as well as collectively exhaustive, mutually exclusive but not collectively exhaustive, collectively exhaustive but not mutually exclusive, or it can be neither collectively exhaustive nor mutually exclusive if a given listing of events is both mutually exclusive as well as collectively exhaustive, then they are said to partition the sample space. So, our next term is partition of sample space. Consider a sample space omega, and let us consider three different events in the sample space a1, a2 and a3. Clearly a1, a2 and a3 are mutually exclusive because the intersection of any two of them is a null set, and they are collectively exhaustive because the union of a1, a2 and a3 make up the whole sample space. In this case a1, a2 and a3 are said to partition the sample space. For the coin tossing example, we define two events, heads and tails. So head and tail are said to partition the sample space because they are mutually exclusive as well as collectively exhaustive. The last term in the list is cardinality of a set. The cardinality of a set is simply the number of elements in the set. For example, if our set omega is h comma t, heads comma tails, because there are two elements, the cardinality of omega, cardinality is denoted by these two vertical bars. So the cardinality of omega is 2. If we define a sample space as 1, 2, 3, 4, 5 and 6 rolling of a die example, then the cardinality of the set is 3. 6. I'm sorry. The cardinality of the set is 6. If we define an event on this sample space, say the even numbers, say 2, 4, 6, then the cardinality of set A is 3 because there are 3 elements in this set. To remember the meaning of cardinality of a set, it will be good to know the meaning of the terms cardinal numbers and ordinal numbers. So just remember, cardinal numbers are those which specify amount, such as 1, 2, 3 and so on, and ordinal numbers are those which specify position or a degree, such as first, second, third and so on. So it is good to know the meaning of cardinality of a set. We will be using it at many places in subsequent modules. So in this module we became acquainted with the terminology used in probability theory. So that's all for this lecture. Thank you.